Thank you for having me. Everyone can hear me okay? Well, it's my first time in Perth, so I'm really happy to be here. I've been to Australia, I think it's my third time to Australia, but it's very beautiful out here. And I did some recon over the past few days, and so you'll see some of those images in my presentation. But the purpose of this presentation is to kind of give you an overview of why are we interested in exploring Mars from a science perspective, from an engineering perspective, and where are we going next? And as all of you are very customer oriented, right? You develop software and applications for your customers. As engineers, our customers are the scientists. So it's really important for the engineering community to understand exactly what the science community needs. So I'll go over quite a bit from a scientific perspective of why we explore Mars. And I think it's also very exciting. And so my background is I've worked for the past 15 years or so in the aerospace sector. I started off on launch vehicles, chemical propulsion, and I shifted over to electric propulsion, which is using plasma to give you very efficient propulsion systems. And then I worked on Mars entry, descent, and landing systems for about 5 years, then Venus entry, descent, and landing systems for a couple of years. Most recently, I've been developing an atomic physics facility for the International Space Station, and now I'm shifting over to Europa landers and penetrating through the ice. So if you have any questions about that, you can ask me during the break too, because I have lots of information in my head that I like to share. But several years ago, I was asked to work on the Mars Science Laboratory Curiosity mission, which was going to send a very large rover to the surface of Mars. And they asked me to be the lead of the parachute system. So I actually didn't have a background in parachutes, but I had a background in aerodynamics. And so oftentimes in aerospace, you can't have an expertise in everything, right? And so I think the gentleman here was talking about multidisciplinary teams. That's essentially what we do in aerospace, is that it's all multidisciplinary. So we have aerospace engineers, mechanical engineers, electrical engineers, computer scientists, physicists, biologists, chemists, all working together in these multidisciplinary teams to be able to pull off very complicated systems. And so one of the challenges of sending something to Mars is actually safely landing on the surface. Of course, there's getting there, which is challenging, but safely landing on the surface is even more challenging just because of the G-forces and the temperature range and the precision which is needed to get you to where you want to go. And so we did create this great movie a few years back to talk through the engineering challenges associated with it. It's called 7 Minutes of Terror. So I'll play that and then I'll talk a little bit more.
When people look at it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun, 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we are facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
A parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
when it opens up that fast, it's a neck snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage away to a safe distance from the rover.
So I think what's so amazing about that is that it's science fiction, but it's actually science fact, right? So that's the engineering system that we developed and successfully landed back in 2012. And you can ask me some questions during the question and answer session as to why did we select that particular architecture. There were reasons for it, but ultimately it allowed us to have the most precise landing possible. So if you think of this as a bullseye of where you want to get to on Mars, more precision gets you to the more interesting places that you want to do science. But let's take a step back, which is why are we so interested in Mars? And so the pictures that you see here, the planet on the left is Venus, which is one planet in from us. The planet in the center, obviously, is Earth, and the planet on the right is Mars. And you can see they're incredibly different from each other now. But what we believe is that at the start of the formation of our solar system, all 3 planets, which we call the terrestrial planets, were actually the same. They all had thick atmospheres. They all had water flowing on the surface. But now, things are quite different. And so I put the stats for the difference between Mars and Earth here. So obviously Mars is smaller, which means it has less gravity. You know, it's got about 1/3 the gravity that you would have here on Earth. Venus, on the other hand, is pretty close. It's about 85% of the gravity that you have here on Earth, because Venus and Earth are around the same size. The surface temperature on Venus is about 475 degrees C, right? That's the temperature of when you try and self-clean your oven. The temperature on the surface of Mars, however, is, it can get up to, minus 100 degrees C. So here you have planets which have evolved very differently over the course of the past several billion years, and we don't actually understand why. And so people oftentimes call the Goldilocks zone, right? So where you have one planet which is hell on Earth, Venus, and then the other planet which is not hell on Earth, Mars, it's very cold. So without understanding how the planets evolve, we actually don't understand how our own planet is going to evolve. And so one of the justifications for going to Venus is that we believe that Venus experienced a runaway greenhouse effect. So all of the oceans basically boiled and then created an atmospheric pressure of 100 atmospheres. That's how strong the atmospheric pressure is on the surface of Venus. So what kind of life forms could survive in that kind of environment? But nevertheless, the planet evolved that way, and we don't actually understand how. So we really want to send a mission to the surface of Venus as well. Mars, on the other hand, now has very thin atmosphere. It's primarily CO2. It's only got about 1% the surface density. The temperature can get incredibly cold during the Martian winters, during the nighttime, and there's no appreciable water on the surface. However, we believe there was in the past. So why these planets evolve this way will enable us to understand how our own planet is evolving. And I'm sure, as it is for your community, understanding climate change is really important. So we can learn a lot from our data points of our neighboring planets to understand how the planet actually evolved. Now, the second reason, of course, is that human beings, the population keeps on growing, so we're probably going to want to expand beyond Earth at some point. And it turns out that Mars is actually a pretty good destination. So on Mars, you've got 1/3 G. Our bodies do like to have some gravity. There's a lot of natural resource available to us on the planet. The length of the day is about 24.6 hours, so it wouldn't be that hard for us to adjust to it. And even though the surface density is really thin, you could conceivably think of ways to pump in CO2 to a higher pressure than walk around with scuba gear, inside of a habitat module or something like that. So you wouldn't need as much oxygen. Or you can come up with ways where you can utilize the surface to make methane for you, for example. I'll talk about that a little bit later. And then the other interesting aside is that you can find places on Mars in the equatorial region during the middle of the day where the temperature is actually around 10 degrees centigrade, which isn't that cold, right? So you can think of how it's far more hospitable to go to Mars than it is to go to our moon, for example, which is a vacuum environment, which is really close to the sun, so the radiation environment is really bad. So there are reasons why we would want to consider going to Mars as a future colonization. And so the way we do that, of course, is by first sending robotic missions so we can develop the technologies and learn about the environment and eventually help us to assess where do we want to land those people when we do want to set up those future human colonies. So those are the primary reasons. But if we take a step back from a science perspective, Mars is actually really, really interesting from a geological perspective. So the picture that you see on the top there is Olympus Mons. You can actually see it from space. It's the largest mountain in the solar system. It's about 3 times as high as Mount Everest. So we know that in the past on Mars, it experienced a lot of volcanic activity, a lot of volcanism, but now it appears to have stopped. Why did that happen? Could that explain why the atmosphere went away? We don't actually know. So part of the scientific method is to create a hypothesis and then to test the hypothesis. And the way the science community is able to test their hypotheses is by us sending spacecraft to orbit the planet and us sending rovers and landers to land on the surface of the planet to take scientific measurements to validate those hypotheses. And another interesting geologic feature on the bottom here is Valles Marineris. It's basically a feature that goes across the center of the planet, and it's Mars's version of the Grand Canyon. It's about 6 to 7 times as deep. So what we do believe is in the past, there probably were appreciable water flows on the surface that created a lot of these surface features. But where did it go? Did it all evaporate into space? Is it frozen in the subsurface? Because if we were to send people there, having access to water is incredibly important, right? You can use it to grow food. You could split it up to create oxygen. So understanding the past and the current geological history of the planet will also facilitate future human colonization. But really, what happened? Why do we think everything changed? We don't know, but one of the hypotheses is that there was a large asteroidal impact with Mars. And so what happens is Mars in the past had a molten rotating core. It had a strong magnetic field. When this asteroid came in and impacted it, it actually disrupted the core, disrupted the magnetic field, and then the atmosphere was ripped away due to in-space radiation, and that's where we are today, unfortunately. So that's a theory. We don't actually know if that's what happened, but we have a mission which is coming up soon called InSight, which is launching actually later this year, which is going to make measurements of Mars quakes, and it's going to make measurements of subsurface temperature, which hopefully will give more data to the scientists to test this hypothesis. So what that means, of course, is that because the core has been shattered, it's not going to come back, and we're stuck with the planet the way it is in terms of what its magnetic field properties are, what the radiation environment is, and the resources which are available to us on the planet. But all of these things are fascinating from a science perspective. And of course, the job of the engineers is to come up with ways to both get to Mars as well as to create instrumentation to make these measurements. So by a show of hands, who many people think that Mars has moons? Anyone here fans of the Expanse series? Okay, good. So you'll reference some of the names I think they actually cover in that series. So Mars actually does have 2 moons. It has Phobos and Deimos, and so these are very small moons, and so that's the reason why they look kind of like oddly shaped, because they haven't compressed into a spherical, differentiated body due to their own gravitational weight. But what's nice about these moons, just like in the Expanse, is that you could actually use them to set up human colonies, because the moons, we know, actually have water ice in them. So you could use this as a mining colony for water, eventually to go down to the surface, or even an in-space depot for missions which are going further into space. You could also use the moons as a communications relay. So right now, around Earth, we have the GPS network, right? That's the most amazing thing ever. We always know where we are. We don't have access to that kind of satellite network around Mars. We do have a few spacecraft, but they die every now and then, because of radiation, because of old age. So if we could set up permanent telecommunications relay on these moons, it would actually give us much more ability to send data and communicate back and forth between Earth, between Mars, and then perhaps missions which go even beyond there. So there are some some architectures which talk about sending people to land on the moons of Mars before we actually send people to land on the surface of Mars. And from a landing perspective, it's actually a lot easier to land on these moons. Maybe hard to stick on them because the gravity is really low, but it's easier to land than going through the atmosphere of Mars, having to slow down that much to be able to land there. So that's a potential architecture that we're looking in future. So who thinks we found water on Mars? I show hands, okay, so you guys are fans. We have, and we found it in different ways and in different places. One of the fun locations, I think, just because I got to work on it a little bit, was the picture that you see here. This white patch that you see here is actually salt water ice. And when the Phoenix lander was coming into land, back in the 2005 timeframe, and the engines are firing into the ground, kicking up all the dust and soil, it actually revealed white patches pretty much just beneath the surface. So we know as you get further away from the equator, there's a lot of frozen salt water ice. And so is that evidence of past oceans on the surface of Mars? Is it evidence of subsurface aquifers with who knows what's living in them? It could be, right? And so going to these locations and making these kinds of measurements gives us the insight into this. And then the other image that you can see on the upper right there is actually of the polar regions of Mars taken by a spacecraft called the Mars Reconnaissance Orbiter, which takes incredibly high resolution images of the surface, down to the meters level, which allows us to basically determine that there are no active Mars civilizations going on right now, unfortunately, that we can see from orbit at least. But hopefully we can create one in the future. But so we do have quite a bit of an infrastructure already set up with the fact that we do have spacecraft that orbit, which provide that telecommunications link, but those spacecraft have a limited life associated with them because they have to carry a propulsion system, and eventually you run out of propellant, and there's no way to service it once that happens. So who thinks, by a show of hands, that we found flowing water on the surface of Mars today? Not as many people know this one. So we actually have, in a way, so you can see in the image here where these are black streaks coming down the sides. This is a cliff face, or the edge of a cliff face on Mars. And because the planet is tilted on its axis, as it goes around the sun, it heats up and it cools down. So if there are subsurface frozen aquifers and they start to melt, some of that water can actually seep out the sides of the cliff faces and run down. So we believe there's actually wet mud. And so if we would love to send a mission in future that goes to one of these places where we know there to be these active sort of mud flows and make measurements. The challenge, of course, is all of those locations happen to be in crater geometries, which are pretty small, on the order of 5 to 7 kilometers. And you have to be able to have something which would either rappel down the side of the crater wall or climb up the crater wall. So there's a whole surface mobility autonomy technology challenge still associated to be able to facilitate these missions. But what's so neat, though, is the fact that there is flowing water in this capacity means that human beings really could tap into this as a resource, and we might be able to find some kind of interesting, precursor life that exists in this environment just beneath the surface on Mars. So we're always learning new information about how the planet is evolving and whether or not the planet is still habitable today. And some of the other images you can see are here. Once again, these are all taken by the Mars Reconnaissance Orbiter. And the image on the right is a false color image to kind of show you where those water streaks are. And I think what's also exciting about this is that this finding of flowing water was actually made by a student, I believe, at Georgia Tech, because all of the data that we collect actually goes online. So anyone has access to it. So anyone can actually do this kind of image processing themselves to make these determinations. So it's very much an open source mentality when it comes to the sharing of science data with the community at large, right? Because this mission isn't for the US space agencies, right? It's pretty much for everybody who's interested in Mars exploration. So how many times have we landed on Mars? We've landed a total of 7 times. Now, this has all been done by NASA. So unfortunately, the Russians tried it several years ago and didn't succeed, and the Europeans tried it twice and didn't succeed. So we get to pat ourselves on the back saying that we did a good job by getting it right 7 times. Although, however, we have failed twice. Once with an Orbiter mission, which became a landed mission, which wasn't supposed to. And then once with a landed mission that didn't work out. And so this is an interesting aside for so there was a terrible problem. I guess this was back just before I started, but there was a unit conversion error. And people were using metric and English units, which is like the greatest mistake you could possibly make, right? And so that's the reason why those 2 missions failed, because of a unit conversion error. So now we do everything in metric, only for spacecraft. Everything else is still in English. Still confusing, right? So it is kind of interesting. But so we've landed there a total of 7 times. The first time was in the late 1970s with the Viking lander mission, which is the picture on the lower left. We landed again 20 years later with the Pathfinder rover. There was kind of nothing happened on Mars for about 20 years, which is the picture on the lower right. Then we landed again in the early 2000s, Spirit and Opportunity. You can see the picture on the upper right there. We landed with that system with airbags, same thing with Sojourner. And then the Phoenix lander, we landed totally propulsively all the way to the surface, which is the picture I showed you before with the saltwater ice below. And then we landed again in 2012 with the Curiosity rover, with a combination of retropropulsive and the Sky Crane. I'll talk a little bit more about that later. And then next up, we have InSight, which is actually going to use a very similar system to Phoenix, and then Mars 2020, which is going to use a similar system to what we did for Curiosity. So we've been there a bunch of times, and each time we go, we learn so much more about how to do a landing system and how to basically advance our technology. So we build off of what we learned. We evolve every single time based off of our prior experience base. And what we really are able to do is we come up with simulations and models. We then validate those simulations and models with these prior missions, which allows us to have a more robust, efficient system. So it's a little bit analogous to what the gentleman was saying before, which is that you always want to send more mass to the surface, but you really want that mass to be payload as opposed to just extra junk because you're not sure exactly what the G-loads are going to be, what the density is going to be. But the same goes for our mobility systems. So this shows you the evolution of our mobility systems over the course of the past 20 years. And we started off with a little Pathfinder Sojourner rover. Then we went to about the lawnmower-sized rover, Spirit and Opportunity, and then we went to the Curiosity rover. And so I went to the zoo yesterday to do some recon to give you things that you would understand about the sizes. And I love the little NumRat, I think it was. So that's about the size of Sojourner, and then you can see the scale of kangaroos relative to the Curiosity rover. And so why do we get bigger? The reason why we get bigger is because we want to be super cool engineers and send bigger stuff, yes, but ultimately we do it because we want to carry more stuff with us, right? Because if you were going to be doing an expedition, you'd want to carry as much equipment as possible, right? So if you have a larger wheelbase, you can carry more scientific equipment. And all the rover is an extension of us. It's a robotic geologist. So we were able to carry a lot more scientific equipment with the Curiosity mission. Plus, the wheelbase is more sophisticated, which means that we can go over more interesting terrain. So if you're going to land in a boring spot, you're not going to find out as much information as if you're going to land in a very, rocky spot with hills and things like that. So we were able to facilitate more access to interesting science and more collection of science data with this larger rover. And we also shifted over to a new power system, which I'll talk about a little bit later. But it allows the rover to operate over longer periods of the day. It allows it to be less sensitive to solar irradiance because it uses a nuclear power source. And it just basically gives you a lot more flexibility. And it demonstrates the technologies, hopefully for future landed missions to the surface. So ultimately, what we're trying to understand as a community at large, right, throughout the world, is whether or not Mars once supported life, whether or not it was habitable, and could it still be habitable today? And so the way you do that is you look for organic compounds, you make measurements of how the different rocks form. Did they form just with volcanic processes, or did they also form in the presence of water? And then you really want to make a measurement of the surface radiation. So have any of you seen The Martian, the movie? Okay, good. So the biggest challenge, in my opinion, for sending people to Mars is coming up with radiation shielding technologies. Because right now we know from the Curiosity rover what the radiation level is, and it's too high for people to go without some kind of radiation shield, but it's not so high that we won't be able to come up with the design of a radiation shield to facilitate it. But you have to make those measurements first. You have to know your environment in order to be able to come up with the next generation of technologies. So in terms of where do we want to go on the surface, so the analog I use here is that if you were an alien race and wanting to explore Earth, would you go to the Amazon? Or would you go to the Sahara Desert to find life? You would go to the Amazon, right? And so we obviously don't have the luxury of the Amazon on Mars, but we do have enough knowledge of the surface from these high-resolution images to say this is probably where bodies of water once were on the surface of Mars. So the science community said we would like to go to a bunch of these places because we think that they probably had either a river or a lake, and where better to look at sort of the evolution of the planet over time than looking at the sedimentary rock layers at the bottom of a water body, right? And so the science community said we'd like to try these places, and then we were able to come up with a design which got them to Gale Crater, which is the picture that you see on the bottom there, which the science community believed was the site of an ancient lake bed, basically a long, long time ago. And so that's what we selected, that's what we designed the system around. Sometimes people ask, well, is there a way for us to go and visit the other rovers? And so as you can see, they're quite far away from each other. So the Opportunity rover is sort of sitting in the middle there, and then Gale Crater's on the right-hand side. So I have a few pet peeves with the Martian. One of them is it's very difficult to traverse those long distances, as he was able to go and pick up the spare parts from the other rovers. Nevertheless, most of what was in that movie was actually pretty accurate. So never the two shall meet. They're so far apart from each other. And ultimately, we send them to different destinations because we're trying to explore the diverse diversity of the planet's surface, right? So even though Mars does look dry and dusty like a desert, it does have very varied geological history depending on where you go. But what was unique about this mission was it was the first time where we were actually able to land where the science community wanted, as opposed to the prior missions, because they didn't have the landing precision. They basically had to do science where we could land them. So it's a very different architecture, a very different model, which facilitates a lot more interesting science information at the end of the day. So this is a sort of a three-dimensional view of Gale Crater. And so what you can see in the black line here is what we call a landing ellipse. So if you had, ultimate precision, you would land on a point, but you don't, because you have variations in atmospheric properties, you have variations in your own vehicle's properties, so you have an ellipse. And so our ellipse was roughly 12 kilometers by 7 kilometers in diameter. And so reference, I went to Google and got an image to show you the scale of what you can see down here on the lower left is roughly where the King's Park is. And then if you go all the way over to the right, that's where the airport is. That distance is about 12 kilometers. So that's basically the size of our landing ellipse. So our design allows us to land somewhere between the edge of King's Park and the Perth airport. And so that was the precision that we were going for. Because if we didn't have that precision, you would either smack into the crater wall or you would smack into the mountain in the middle. So that's why you have to have that landing precision or you're going to not survive, basically. Or alternatively, if you don't know where you're going to land, you have to have a mobility system which can drive for many, many hundreds of kilometers, rappel down the sides of mountain ranges to get you to where you want to go, which is also a bit of a challenge. And so having the landing precision is obviously a more efficient way of doing it. And once again, we believe this site was the site of sort of ancient river body. So as a comparison for how our precision has improved over the course of the past, I guess, 40 years or so, is the outer ellipse that you see there was the Viking 1976 mission, almost 200 miles in the long axis of the ellipse. They basically had no precision, right? 200 miles is a long way. Move forward 20 years, Mars Pathfinder, they got a little bit better, roughly down to 140 miles or so. And then move again over to Phoenix, they got it round even smaller. But you can see Curiosity is basically 2 orders of magnitude improvement in landing precision over these prior missions, because we came up with a whole suite of new technologies to facilitate that. And so once again, I have to give you a reference. So in terms of the landing accuracy for the Viking missions and the Mars exploration rovers, it's basically the distance between Perth and the sort of the southern end of the tip on the edge of Western Australia, as opposed to landing within the region of greater Perth city center, right? So that's a huge improvement of being able to know where you want to go, as opposed to being somewhere on the edge of your country and then driving in for years and years and years to where you want to go. And so for reference, this is an interesting aside, the rovers drive really slow. And the reason for that is that their computer computational power is abysmal. It's in the megahertz range, because space-based computing is not the same thing as commercial computing, because you have to be radiation tolerant and radiation hardened. So like my iPhone or my Samsung Galaxy phone has probably 2 orders of magnitude more capability than a space-based computer. So you have to have a justification for coming up with a new computer technology, and right now we just don't have any reason to develop it, because we don't have to drive really fast. But the rover actually drives incredibly slow because of the image processing that it has to do for hazard avoidance, and therefore it can't go that fast. So therefore, you can't have an architecture where you have to drive, over hundreds of kilometers to get to where you want to go. So yeah, and this once again, just to show you the reference of basically this is the area in which we have to land it in order to be safe and not get damaged by the sides of the crater wall. So I'll talk a little bit about the actual landing system technology and walk you through it. See if this video works. Okay, so the purpose of an inter-descent landing system through a planetary atmosphere actually primarily uses the concept of aerodynamic drag, because there is an atmosphere. So the atmosphere is like your propellant. So that atmospheric drag takes you from around 13,000 miles an hour to around 1,000 miles an hour. At that point, you hit terminal velocity. You have to basically do something else. You open up a parachute, which is an enormous parachute because the atmosphere is really thin. That once again, eventually you'll hit terminal velocity. You get to around 250 miles an hour. Then you can't go any slower. So you actually cut the parachute away, and you have to do the rest of your descent on retro buckets, basically to take you from 250 miles an hour down to around 2 miles an hour. So we did a trade here as to whether or not to descend retropropulsively all the way to the surface, and we chose not to, and there's several reasons for it, but the primary one is now your rover is your lander. Those engines that are pluming into the ground, there's a nice big distance between the engine plume and the soil, which could eventually cover your rover in dust if you didn't do it that way, and you can carry less propellant. So this was kind of the most efficient way to do it, to land it safely on the surface. Now, there is waste in the sense that that whole vehicle is done its job, turns 45 degrees, flies off, crashes, and it's done. But now the rover has actually landed safely on the surface. But ultimately, the entry, descent, and landing through a planetary atmosphere is about managing your drag, right? Because you want to use the atmosphere to slow you down if at all possible. But of course, the problem with that is that just like when you rub your hands together, they get warm. Think about that, but reaching the surface temperature of the sun. So as a result of that, you have to have something called a heat shield, which protects the rover in the interior from burning up. Now, the other aspect of this mission is that this is basically the entry vehicle. This encapsulates the rover. So this is what generates the aerodynamic drag because of its odd-looking bowl shape. But it doesn't look as though it's very aerodynamically efficient. It isn't. And so it kind of looks like an emu. It can't fly, right, because it looks kind of ugly, although I think the emus are really cute. But in reality, it's more like a bird because even though it does produce a lot of drag, you can actually give it an angle of attack. So it actually has a lift-to-drag ratio. So this vehicle is actually an airplane, a horribly inefficient airplane, but an airplane nonetheless. And what that means is that it generates lift. So if you can modulate that lift vector, you can actually fly it around. And so it generates lift because it's got an angle of attack. So it's flying down, and we have little thrusters on the backside that we fire to roll it around, and as we do that, we shift the lift vector around. And of course, all of this is being done autonomously, right? So that's where guidance, navigation, control is software in the loop. There's no communications, other than one way back to Earth whilst this thing is going through the atmosphere. So all of that is done with the onboard computer. All of that is done with onboard sensing, with algorithm in the loop to be able to fly us to the final destination. So there is a certain element of it which is sort of predetermined. Like we're not actively selecting a landing site, for example. That's what we're doing in the future, and I'll talk about that in a little bit. But that's ultimately how we were able to get the landing precision that we wanted, was because this is a little airplane that flies itself to a smaller landing ellipse than ever before. All the prior missions did not have an angle of attack, therefore they didn't have the ability to rotate their lift vector. So I've been asked this before, which is, do we use agile? And I'll be honest with you, we don't really use those terms in the aerospace industry, so I Googled agile, and Google must have figured out what I was searching for before, because this is what I got, an agile kangaroo. So I thought that was the cutest thing ever. Actually, I think they said it was an agile wallaby. But so do we use agile? So in a sense, we can't, right? Because when we build a system, the first time we truly test it end to end is on landing night, right? So therefore, we can't go through a cycle of, we'll do this, we'll do that, we'll do this, do that. However, we do break it up into phases. So I'll show you that next. We break up the entry, descent, and landing segment into phases. So this is kind of like a 2D view of that. You start off with a hypersonic descent portion where you're basically going from 13,000 miles an hour to 1,000 miles an hour using a heat shield. You then do the supersonic section where you go from 1,000 to 250, and then you do the retro propulsive system. So each one of these things is a separate team. Each one of those teams does go through a design cycle. So each one of those teams is constantly doing trades. And in some cases, we do prototyping, like hardware prototyping, and test it. In some cases, we can't. So we'll just do sort of test coupons. Like for a heat shield, you can't actually test a full-size heat shield at the Mars entry conditions. It's impossible. So all you can do is like build little test coupons and then stick those test coupons together to make a full heat shield, and then you send it off to Mars. So the challenge, of course, for what we do is that it's impossible to do an end-to-end test on Earth, because on Earth, the gravity is 3 times as high. On Earth, the atmosphere is primarily nitrogen, not CO2. So there's absolutely no way to demonstrate our system end to end until we actually take it to Mars. But we can be really smart by understanding the physics associated with it, having the appropriate engineering margins, and doing our design cycles, which we do actually. So there is an element of agile to what we do. It's just not in the same sort of end product atmosphere, because we're not a commercial kind of entity. But nevertheless, you can see the analogy there. So what I would say is more agile-like is parachute testing. So I'll show you a video of that. And so this was one of many tests. We had several failures, and this was the 3rd time around where it actually did work. So we do that. So when we look at it from the subsystem perspective or individual hardware element perspective, then we do these design cycles, and we launch it, and we launch it, we launch it until we get it right. So that's an example of what we do with parachute. So it took us many attempts to get to this point because we didn't have enough. We try and make things as light as possible, and then you have to eventually need to add a little bit more mass, so that you can get the thing to work from a structural perspective. And then another aside, which I like to talk about, which is diversity, which is the absence thereof diversity in this picture. And sadly, and I think probably you all know it, I would say there's not a good representation of women in certain elements of the STEM fields, aerospace, mechanical, electrical, computer science. So we really do need to make an effort to make that better. And so that means both in your hiring decisions and encouraging, the women in your life to pursue these careers, whether it's sisters, daughters, cousins, that kind of thing. So it's really important to get diversity. And the reason why I say this, because you can think about it logically. If you had a team where everybody was a clone of each other, they would all come up with the exact same solution, right? So when you have people from diverse backgrounds, whether it's from other countries, different ethnicities, different walks of life, they have different ways of solving problems. And you can come up with really interesting solutions. So even though we may not have a good female component, we certainly do usually have a pretty good mix of people from all over the world in what we do, at least where I work. So I think it's nice because everybody brings something to the table, and it makes it a much more enjoyable work environment, to have that kind of diversity, in my opinion. So what is the future? So the future is basically, how are we going to get more mass to the surface of Mars? How are we going to be able to survive on the surface of Mars for longer periods of time? So even though what we're doing primarily is for robotic missions, there's definitely dual use for robotic missions as there are for human missions. So for example, with our particular rover, we shifted over to something called an MMRTG, a multi-mission radioisotope thermoelectric generator. So this is a way of producing electricity using plutonium thermal decay, converting it into electricity, and using that as your power source. You no longer have to have really large solar arrays. You no longer have to worry about the dust depositing on your solar arrays. And one of the rovers actually died, unfortunately, because its solar arrays got so covered with dust, when it got stuck in something, it didn't have enough energy to sort of back itself out. So that happens over time. So when you have something like this, the decay rate is pretty low, so it lasts for an incredibly long period of time. So our technology development in this area is completely directly relatable to future human missions, which also require this kind of thermal energy conversion into electrical energy conversion. The more efficient you can make it, the more power you have available to you. Right now, it's not that efficient, but we're working on getting that better. So Mars essentials. So if you are traveling to another planet, you probably want to carry a bunch of science equipment with you. So a lot of our science equipment was related to imaging. Imaging for image processing for hazard avoidance was a large portion, right? Because we don't want to drive off a cliff or drive into a rock. And we don't have somebody with a joystick driving the rover, back in Los Angeles, because there's a 14-minute time delay. So the rover we basically say, rover, today you're here, go over there, you figure it out. And so it actually does that by digital image processing for its HazCams, basically. So, and then it will send data back and stuff like that. So it's basically executing the sequences that we give it, but it's smart in that sense, right? So it's not a dumb rover, it's a smart rover in that sense. But it also has a lot of scientific equipment, and the purpose of most of the scientific equipment, of course, is to understand the composition of the atmosphere and the composition of rocks, both from an elemental perspective as well as from a molecular perspective, because there's a lot of information that you can get. And there's different ways of making those measurements, all which is done real time with the rover on board. But of course, what would be your science instrument of choice? Little kids love this. A laser, of course, which it does have. Of course, it doesn't create as much of a disastrous effect on the surface of the planet because there's not that much oxygen there. But the laser is pretty powerful. So the whole purpose of the laser is to burn a hole in a rock. So if you stood in front of that laser, it would definitely burn a hole in you as well. Not all the way through you, but you probably get damaged. So you wouldn't want to do that. But nevertheless, you use lasers to vaporize material, which then generates something called a spectroscopic signature. That spectroscopic signature you then look at with a detector, and then you can tell what it's made out of. So it's actually a very robust way of making this measurement again and again and again. So that's our primary mechanism for determining elemental composition, is using laser-induced breakdown spectroscopy. So how did we get to Mars? Well, I showed you the picture before of the Aeroshow, the entry vehicle. So that yellow-looking thing you see there is basically a heat shield. So what you can think of a heat shield is when you light a match and the tip burns, the heat shield is kind of like that. It burns up, and the energy is absorbed that way, and it sloughs off, so that what's inside of there never actually sees the temperature differential, and is always kind of kept at room temperature. So that's kind of the architecture of how you keep yourself safe when you're entering through that really high temperature environment. Now, in terms of how we get from Earth to Mars, first we go up in a launch vehicle. That was back in November of 2011. And then we have an in-space cruise stage, which takes us basically to not a Mars orbit insertion, but pretty close to Mars. And then we actually just release from the cruise stage, and it enters the atmosphere, and its trajectory is basically pulled in due to the gravitational well of the planet. So how long does it take to get between Earth and Mars? another good analogy. The gestation period of between a two-toed sloth and a human baby. So I did check on that. There's some type of sloth which I think have more like 14 months, but this particular sloth apparently is very similar to human baby gestation period. So for small children, they think that's the worst thing ever. It's like an entire school year. But for people as you get older, like, yeah, it's not so bad at all. I can handle 7 months next to somebody I didn't like, maybe. So now this is, in addition to this being really cool, there's a reason why we did this. So this is the first time we actually had a camera on board the rover looking down as it was descending towards the surface of Mars. So what you just saw was the heat shield falling away, which allows the radar to actually see the ground and make measurements of velocity and altitude. And so what you're seeing right now is the rover, as it was descending, and it's like rocking back and forth. The reason for that is because it's under the parachute. So the parachute has this sort of generic oscillatory motion that you see in the subsonic environment. And so now you can see like the darkened regions, those are actually ancient volcanic deposits on the surface of the planet. You can see other pockmarks. These are craters within Gale Crater. But eventually what you'll see is that it will stop rocking back and forth and it'll kind of shift off to the side. That's because the parachute's been cut away and it starts that inert maneuver so that you don't have a recontact between the parachute and the vehicle. But we get so much interesting information from the image processing here, right? Because we can see the feature size getting larger, which also gives us an indication of what the altitude difference is. The motion back and forth, if we have some kind of known fiducial, will tell us what the angular rates are, right? So there's so much information that can be obtained from video processing if you can do it real time and fast enough. So now what you see is we're on the Sky Crane, the retro rocket's getting closer and closer towards the ground. And so what you're going to see eventually is you're going to start to see some gas and some dust. So this is because the engines are actually intersecting with the ground and kicking. So take a water hose, you put it into a sandbox, it kicks up everything, right? And so now what you see is the rover's wheels have come down, they've kind of fallen to the view, and you can no longer see the ground now because there's so much stuff being kicked up. But this sequence was all done autonomously by the rover. So it was collecting diagnostics related to altitude, horizontal velocity, vertical velocity, and then executing a pre-planned sequence based off of sensing different targets based off of that measurement of basically integrating acceleration. So the very first thing that the rover had to do based off of its programming when it landed was to send a picture of itself to say that it landed safely, and we'll talk about a little bit later. But the reason why that was important is that that was a technology demonstration for terrain relative navigation. So that camera system, when you couple it to a map of the region where you're planning to land, because we have great high-resolution maps from HiRISE, it then is able to take a look at certain surface features and say, oh, I'm in the vicinity of that surface feature, or I'm off by this much, and actually vector or change the throttle level of different engines to get it closer to where it wants to go. So that demo that we did on that mission is now baselined for the next mission so we can actually get a more precise landing location using that image processing in the loop on board to get us to an even tighter landing location, which is great, right? So that's kind of what we do is you feed forward for the next mission, you demonstrate a technology, and then you launch it in the future mission. So it's a little bit different than your Agile, but still I see the relationship between the two. So the very first image that we got back after Curiosity landed was a picture of Curiosity, so you can see its shadow, and then you can see Mount Sharp in the distance, and so it looks pretty awesome, right? And the picture on the right is a color view of what the landing site looks like. And so for any of you who have been to the desert here in Australia, it is kind of amazing how even though it's another planet, it looks just like Earth. That's because our planets are all really similar to each other, right? So, so even though they are different worlds, they're not really that different from each other. Of course, there's no oxygen, so you wouldn't last too long if you didn't have some kind of pressure suit on when you're out there looking, but still, it's pretty cool. Now, simulations versus reality. So if you're really going to nerd out about what you've done, you want to know how good of a job did I do, right? Everyone wants to know how well they scored on a test. And so what you see in the lower image there, a red ellipse, it's kind of faint. That was our predicted landing ellipse from our Monte Carlo simulations. That white box is actually where we landed. So we did a really good job in terms of predicting our performance, which means we have good models for the atmosphere and we have good models for the vehicle performance, right? So if it was a really, really bad day on Mars, right, the winds were higher or the density was much lower, we could have landed somewhere to the edge of that ellipse. And that actually is what happened to the Phoenix lander back in 2005. It actually landed close to the edge because it was a bad day on Mars. And you can't design a tank because you'll never get anywhere. So you have to design it within a certain probability of success, which is like usually 95%. So you do have a chance of it not being successful. So this is another post-landing assessment. So we were able to take the Mars Reconnaissance Orbiter and shift it into position so it would actually capture the descent of the Curiosity rover under the parachute. So we actually got this image, which is pretty amazing, right? So this is descending a body on another planet, 400 million miles away. It's pretty awesome. So autonomous systems. So once again, the rover, we don't drive it. We simply tell it where it needs to go. So we actually have to have autonomy on board. And so there's some interesting things to say, which is the wheel that you see there has a particular marking on it. The marking is a fiducial. So once again, we use the fiducial to say, this is basically, sort of my position, the size, and my image plane of what I'm looking at. Therefore, I can use that as a means of saying, getting this image, how much further do I have to drive in a particular direction, right? Because we have it from different views, different cameras, so you can create like stereoscopic view of it. Now, of course, it also spells Jet Propulsion Laboratory in Morse code. So that was our way of sneaking that in there so that it's ingrained on the surface for all time for future alien civilizations to know what we did. But still, at the same time, it has an important engineering purpose as well. So we get to get both our to kill two birds with one stone. So intelligent systems. And so some people say, you ever heard of the movie Capricorn 1, where people didn't land on the moon? So people are like, how does the rover take a picture of itself? It must not have actually landed. It's sitting on a Hollywood lot. But we have enough pictures that we're able to piece together a 360-degree view so that the most important thing that everybody needs to do these days is to take a selfie. So this is a selfie. I couldn't, when you type selfie on Google, you don't want to put most of those pictures in public company. So I found one with a dog, which is more appropriate. But this is actually also useful, right? Because now we can take a look at the health of the overall rover. And so we can see how much dust is depositing. So getting dust deposit actually changed the thermal property because we put white paint on there, not just we like white looking cars, right? But because the white paint has a thermal purpose. It actually controls the alpha over epsilon ratio. It controls how much radiation is absorbed versus how much radiation is emitted. So we need to understand how the rover changes over time. The wheels themselves, we keep a track of their properties. They're made of titanium, so we can actually see holes that are starting to form. So all of this image data is important for assessing the health of the rover and then deciding what we're going to do with it next. So, of course, the question becomes, is there life on Mars? And I'm a cat person, so I had to show that. But it's very cute. So what is in the future? The future is making an assessment of landing sites. So I talked about this before. This is the laser-induced breakdown spectroscopy. That's the hole that we burn in the rock. It generates the spectroscopic signature, which then tells us what it's made out of. So it happens rapidly. We do it again and again and again. So we're constantly making these measurements. Understanding the environment, we have a weather station, which allows us to validate atmospheric models on the surface. Winds, temperature, pressure, and the really important graphic is the one on the lower left there, which is the radiation level. So now we know what the surface radiation levels are, so we know how much shielding we require for future, spacecraft missions as well as future human missions. That's actually kind of mission enabling. And then where do we want to go when we actually send people there? We actually have found that there's methane being released into the atmosphere on the surface of Mars. And so if we can pinpoint the locations of where that methane is coming from, we probably would want to go there, both for scientific reasons and because perhaps we can use that methane as a power source, for example. So all of the data that we collect helps facilitate the future human exploration. So I'm running out of time, so I'm going to go through these last few relatively quickly so you can ask me some questions. But the future is getting larger payloads to the surface. Larger payload means more mass, bigger area, so that we can actually carry people, right? Our systems for robotic missions are not enough to carry people. So that means propulsion systems. And that means deceleration mechanisms, not parachutes, something completely different, inflatable deceleration mechanisms. And then vehicles which can handle even more precise flights. Because if you're people, you'll want to land roughly in probably like a 10-meter area, not a couple of kilometer area. So you have to have much more precise landing systems. So once you get there, you have to have environmental control systems, which one provides you a pressurized environment, provides you oxygen and nitrogen, and it also provides you radiation protection. And so I know there's certainly a lot of work which is being done now from a human factors perspective, which is great, but we also have to develop the technologies to make sure that people can survive in a very challenging environment. Not as difficult, I would say, as the space station from a pressure perspective, but very difficult because of the radiation environment. We have to have surface mobility systems, which have to have all the same life support capabilities as a non-mobile system, which is very challenging. And then the most important thing that we have to do is something called in-situ resource utilization. So we want to be able to create our own power, whether that be with solar array farms on the surface or the production of methane, which you can actually get using CO2 and hydrogen if you bring some of it with you. We want to look at radiation protection. You could conceivably use the soil to as sort of like a radiation protection layer. So you actually put the habitats under the ground. That's another way of utilizing the planet to help you. Water. getting access to those subsurface aquifers. And then extremophiles is basically a type of plant which can be grown in a very low oxygen environment, primarily CO2 environment. So the big takeaway here is if you're going to Mars, you're all going to be vegetarians, which is great. I'm a vegetarian. But because you're not going to be bringing cows with you. Or they actually starting to sell this fake meat now in petri dishes, so I guess you can eat that if you're there. But other than that, you'll be eating vegetables. And if you saw the Martian, fertilizing them with your own stuff. So that's kind of the future. And so ultimately, you have to really think about it. Would you want to live on Mars? Would you want to be part of the first set of colonists that go and live on another world? Because once you go, you probably won't come back in the sense that when you are okay, but when your children are born there, they're going to be born in a very different environment, right? They're going to be born in a different radiation environment. They're going to be born in 1/3 G. So when they went to Earth, it would actually be really hard on their circulatory system, for example. So it's kind of it's not a one-way journey in the sense that you can't ever come back, but it may be a one-way journey because you really can't come back because your body's not set up for it. So, and I think the really important takeaway, and I like to give these talks, is that everything that we do is for science. Everything that we do actually trains the next generation of scientists and engineers. The space program in general motivates a lot of people to become scientists and engineers, so I think that's kind of a great thing. And then all the data that we collect is publicly available, so anybody can analyze it, have access to it, and be engaged in it. So, because if we're going to go to Mars, it's not going to be the US Space Agency, it's going to be all space agencies getting together to fund something like this. So I think I probably have 5 minutes for questions. So I'll take questions. Thanks.